When a force is exerted on a spring, it will either compress or stretch the spring if it is pulled or the weight is hung on it. Some objects, like bridges, will also behave like springs. When a weight is placed on a bridge, parts of it will be stretched and under tension. Other parts will be squashed together or compressed. In compression, the particles making up the material are pushed very slightly closer together. But mainly it is the side under tension, where the particles making the material are pulled slightly further apart, that allows the plank to bend. Imagine measuring the extension of a spring when different loads are hung from it. The extension of a spring is found by subtracting the original length of the spring from its length with the force applied. 2 newtons force extends the spring by 2 cm, 4 newtons by 4 cm up till 8 newtons and 8 cm. Hooke's law states that the extension is directly proportional to the force applied, provided that the elastic limit is not exceeded. At the elastic limit, the spring becomes overstretched and won't return to its original state. So to recap, the straight line shows that the extension is directly proportional to the load on the spring. That means the extension will double if the force doubles, it will treble if the force trebles, and so on, until the elastic limit is reached. This relationship is known as Hooke's law. There is a linear relationship between force and extension. Here is the graph we get if we perform the same experiment but use a rubber band instead of a spring. The results with a rubber band does not give a straight line graph. As weights are hung on a rubber band, to start with, there is hardly any stretching. Then it stretches a lot before almost stopping as the band is extended fully. This is an example of a non-linear relationship, and the band doesn't obey Hooke's law. This machine, called a bull worker, is used to exercise muscles. When the ends are pushed inwards, the spring inside is compressed. The bigger the force, the more the spring is compressed. If the force is gradually reduced, the spring expands until it regains its original shape. The spring is showing that it has elastic properties. The extension returns to zero. We can see this at the origin on the graph for the spring experiment. This spring obeys Hooke's law. When the weight and the upward or restoring force are equal, the spring is said to be in equilibrium. The spring constant K is a measure of the strength of a spring. It measures the force or the number of newtons it takes to stretch the spring by 1 meter. Which is the weakest spring, A, B, or C? Pause the video while you think. Well, C is the weakest spring, needing only a small force to make a big extension. And which spring will store the most energy if they are all extended by the same amount? Spring A will store the most energy because it needed the largest force. Let's look more at the stored energy. When we stretch a spring, we can change its shape. We are doing work. The spring can then go back to its original shape and the energy stored in it is released. The amount of elastic potential energy stored in a stretched spring can be calculated using this equation. Elastic potential energy equals 0.5 times spring constant times extension squared. Assuming the spring obeys Hooke's law, where elastic potential energy E is measured in joules, spring constant K in newtons per meter, and extension E in meters. Let's try applying this. A spring is stretched. It has a spring constant of 3 newtons per meter. It is extended by 50 centimeter. What is the elastic potential energy stored by the spring? Pause the video while you work it out. How did you do? So that's everything you need to know about the springs and their extension.